Hello, my name is Gabriel Tidy, and I will be giving a presentation based on a research paper I wrote for partial fulfillment of an honours degree from the School of Computer Science and Applied Mathematics, University of the Witwatersrand. The title of the paper is Reward Structures for Robotic Locomotion Tasks Using Proximal Policy Optimization. This presentation is a high-level summary of the paper. If you're interested, I encourage you to check out the paper itself for more details, especially details of technical implementations. First, I will motivate what problem the paper tackles, why it is important, and what was done to solve the problem. The key use of robotic locomotion is as a substitute for human tasks that are particularly dangerous, unsanitary, or repetitive. Robotic locomotion tasks are widespread and popular in fields from surveillance to transportation to emergency rescue operations. The skills for robotic locomotion can be coded by hand, although this is extremely time-consuming and often impossible to implement correctly. Instead, the skills are typically learned through reinforcement learning, which requires carefully designed reward structures. However, little research has been done on reward structures for robotic locomotion. This paper attempts to fix this by designing, implementing, and testing various reward structures for these tasks. In order to evaluate the reward structures, a novel evaluation metric is also introduced for measuring safety in robotic locomotion, namely the risk score. I will now provide a brief background on reinforcement learning and the role of reward structures. Reinforcement learning is a type of machine learning, and it differs from other machine learning methods as instead of learning through gold standard examples, an agent learns through its own trial and error interactions with the environment. The agent is not told the best actions to perform during training. Instead, it is given feedback on its own chosen actions in terms of rewards. The agent learns based on these rewards, which guide them to finding the best actions to perform. However, if an inappropriate reward structure for the task is used, this will cause at best long training times, and at worst, completely incorrect behaviors to be learned. This paper specifically uses proximal policy optimization, a popular algorithm for reinforcement learning tasks. However, the specific algorithm used is not important, and insights gained from the reward structures implemented in this paper can be applied to any reinforcement learning algorithm for robotic locomotion. I will now dive into the core implementations of this paper, namely the reward structures that are designed and how they are evaluated. Good locomotion should be fast and safe, but there is often a trade-off between them. The faster you move, the less safe you are. A variety of reward structures encouraging these behaviors are implemented, with a total of 8 types of rewards. Each reward structure provides a positive reward based on the agent's forward velocity. The faster it moves, the more it is rewarded. There are 4 primitive rewards, which are the baseline reward, which only considers forward velocity, the conservative reward, which also provides a negative reward based on the amount of joint usage of the agent, as more joint usage typically leads to potentially unsafe and extreme movements. The scared reward, which also provides a massive negative reward whenever the agent flips upside down, as flipping upside down means the agent can no longer move forwards, and in addition could also cause potential damage to the robot. And finally, the survivor reward, which provides a small positive reward for each action taken that does not cause the agent to flip upside down. There are also 4 combined rewards, which use elements from the primitive rewards they are based on. These are the conservative scared reward, which penalizes joint usage and flipping upside down, the conservative survivor reward, which penalizes joint usage and rewards not flipping upside down, the scared survivor reward, which both penalizes and rewards flipping and not flipping respectively, and finally the conservative scared survivor reward, which considers all the metrics used above. The reward structures are evaluated based on the speed and safety of the locomotion they produce. Speed is measured by the agent's average forward velocity, and safety is measured using the novel risk score, which considers the average vertical velocity of the agent and the average angular velocity of the agent's torso. High vertical velocity values indicate rapid movements up and down, or the agent jumping high into the air, both of which can potentially cause the agent to flip upside down, or can cause direct damage to the agent's joints. High values of the agent's angular velocity indicate rapid twisting or turning, which likewise are a potential cause of the agent flipping upside down. I will now speak on the experiments run to train and test the reward structures, as well as the training domain used for the experiments. This paper makes use of OpenAI Gym, an industry standard for reinforcement learning tasks allowing simulated agents to train in a variety of environments. Specifically, the MuJoCo or multi-joint control environment is used. This is a realistic physics-based environment for training 3D robotic agents. The agent used is the quadrupedal ant robot, a legged robot with 4 legs and 2 joints per leg. An image of the ant robot is shown here, taken from one of the trained runs from this paper. Training the agent using each reward structure was done 3 times each, with each of these 3 runs tested 10 times and the average of the results used. This is done to eliminate variance from the results, and to see how each reward structure produces locomotion that is consistent or not. I will finally dive into the results obtained from the experiments and what they mean for the implemented reward structures. First, we can see a plot of the agent's returns and losses over time during training. Returns are a measure of the expected future reward of the agent, and as such should increase during training. Loss is a measure of the error of the agent's actions and how it evaluates certain states of the environment, and as such should decrease during training. From these results, we can see that the agent is able to achieve learning using each reward structure, except for the baseline reward, shown in blue. We can see this as each reward structure shows some increase in their returns over time, except for the baseline reward, which remains constant. This is likely as the baseline reward does not consider enough information, as it only uses forward velocity and no safety metrics. Here we can see the main results for this paper, shown in a plot for each of the 3 runs using each reward structure. The plot shows the risk score compared to the speed for each run. We can further see the poor performance of the baseline reward here, as well as of the scared survivor reward, shown in blue and pink respectively. Although these rewards have good risk scores, their speed is likely too slow to be useful in practical applications. The poor performance of the scared survivor reward is likely due to it heavily penalizing flipping upside down, and providing rewards for not flipping. As such, its trained behavior is very conservative, and extremely slow to ensure there are no flips. We can also see the default reward from the training environment, shown in yellow, which surpasses the speed of all reward structures implemented in this paper. This is likely as the default reward has access to contact force information, which is not available to the rest of the rewards, and as such, it is able to learn better behaviors. However, some of the rewards come close to matching its speed, such as the conservative survivor reward, and many obtain better risk scores, such as the scared and survivor rewards. This means the reward structures from this paper are still useful in tasks where safety is a priority over speed. In addition, it was expected to see a trade-off between low risk scores and high movement speeds, as the faster you move, the less safe you would be. On the contrary, some rewards, like the default and conservative survivor rewards, achieve very good speed with relatively low risk scores. This indicates that a lower risk score can allow locomotion that is more stable and therefore faster. Here we can see videos from trained runs using the best and worst performing reward structures implemented in this paper. On the left we see the scared survivor reward, which although safe with very low chance of flipping over, moves extremely slowly. On the right, we see the conservative survivor reward, which moves quickly and with relative stability. Thank you very much for viewing this presentation, and if you would like to see more, I encourage you to check out the entire research paper available at the link on screen.